population impacted by this event. So if you have elderly populations that have to go to Arafat on the triangle the mountain of Arafat, I think it's called, and they have to be outdoors. There's no choice. Basically, you have to be outside. And if that falls, that's all tied to the lunar calendar. If that happens to fall during the summer years, then people could be at risk. How much time do I have? Okay. This is, and I'm not going to spend time on this, but this is, well, I will spend time, but I'm not going to spend a lot of time on it. This is an event, return period versus wet bulb temperature. And I just focus, this is South Asia, okay? There's that Ganges Valley, there's the Indus Valley here. And I'll just pick Patna, okay? Which is in Bihar, India, part of the, which you can't really see, but just making an event here. So Patna is part of the Ganges Valley there. And I just picked what the current 100-year event is. Okay, so some of you aren't familiar with return periods. Okay? A 100-year event is the event that has a probability of 1 over 100 or 1% of occurring. So on average, it occurs once every 100 years. A 50-year event would have it occur on average once every 50 years. Okay? So I just take the 100 and just a empirical return period analysis. And the 100-year event, we take that down and then project across. The 100-year event in the future, so this is the present day 100-year event, is about 32 degrees. Okay? So the current 100-year event in this particular location in Patna, India, is 32 degrees. Right? In the future, that event occurs every roughly 3 years. Okay? So a 100-year event just became a 3-year event every 3 years. That's quite remarkable. We can look at all of those. Okay? So look at any of these. We just drop down the 100-year event, and we come across. Okay, so this is sort of mountain region. If we look at Lucknow, for example, in the valley, or 100-year event, we get used to something like a 2, 3, 4, 5-year event. It comes close to 10 times more. Under mitigation, that 100-year event becomes more like a 10-year event. Okay? So even under mitigation, we have a 10-fold order of magnitude increase in probability of this occurring. Again, back to our vulnerability plot, basically we have high population densities, low GDP per capita, and high agricultural intensity. So again, lots of people, roughly 1 billion people in India, very poor, no air conditioning, things like that, and working in the fields. Okay? Most of the population is working in the fields. Okay? Let's look at this in a. We basically took this and looked at it in 3 different ways. And I'll just show one example here. This is population exposure to maximum wet bulb temperature. So this is just the maximum, say, 100-year event roughly. Okay? It's really like a 90-year event in this case. 90-year event. Okay. 35 degrees, 3% of the current population impacted, or sorry, future population impacted. 3% of the population would see a 35-degree event on average once every 100 years. Not very much, right? 3% is low once every 100 years is a low probability. Okay, but it still happens. We still get 100-year events, and we have 3% of the population. If it was 3% in a billion, which might be 2 billion in 50 years. What's 3% of a billion? Okay, I think that's what, 30 million? 30 million people. If they're not indoors, 30 million people would die. And that's, when I say that, I feel like I'm exaggerating, but it's just, still what it happens. There's no way around that. Okay. If we look at population exposure to median maximum temperature, so this is like sort of every other year, we get a 2-year event, so every other year, and we took that 31, that extreme danger threshold by the Weather Service, and we have every year 30% of the population being exposed to extreme danger. Just picking out numbers and look at it in different ways, no matter how you look at it, it's bad as that. Okay. Agricultural land. Okay. This is actually a surprising one to me. 31 degrees 70% of the land every other year would get impacted by extreme danger conditions at these points in the season. When do they do their agriculture there? They do it when the rains occur, and it occurs during the monsoon season. They do have irrigated agriculture as well. But that's the monsoon season occurs in June, July, and August. And that's when you Okay, this is a study that just came out a week or two ago. Climate change impacts on Southern California water resources. I added these in just before. Someone asked a question about using a model to look at water resources with flooding. So I thought, well, that would be relevant. So this is our water resources in the western U.S. are very complex, and they're very largely dependent on a very complex reservoir system we have there. We have hundreds of reservoirs, and we have a lot of snowpack. Snowpack is a natural reservoir for us. It's a warmer temperatures we look at snowpack are natural reservoirs melting. We have to figure out how to store that water. Okay. But I'm just focusing on the extremes here because I don't think you guys care that much about snow melt. Or, and I know you do have reservoirs here, but you're going to be more interested in flood events because that's what impacts our communities more close. I don't think we might have problems with water supply. I think it's probably more on water quality here, but water supply is probably fairly good. I'm not sure about that. Okay. And this is daily maximum precipitation. So this is our 50-year event, the event that occurs on average once every 50 years. How does that change in the future? So in the present day, this event, this 50-year event, becomes something like, we call it, if you look at the Los Angeles or Southern California basin here, so this is all Southern California where we are, here's Loyola Marymount University, and that becomes this shade of blue. Maybe the 100-year event becomes something like a 20-year event at Loyola Marymount University. So instead of occurring, 50-year event, instead of occurring once every 50 years, it occurs once every 20 years. Here in San Diego, that might be once every 5 years or 10 years. So the current 50-year event and other variants is projected to occur on average every 10 years or so, 2050 plus or minus. In some regions might be 5, other regions might be 20. Okay. For us, okay, in terms of water resources, which really is my expertise, for us, what does that mean? That means our reservoir water levels, we have to put them in the flood control. So we use our reservoirs to store water, but we also use them for flood control because all our rains come in the winter time. They are winter, so mainly December, January, February. Plus or minus. And most of our reservoirs have to be in flood control mode at that time, but they also have to store water for our communities. Okay. So if we have greater floods, we have to lower those reservoir levels, which means we're losing water that we can use for human use. And in urban environments, okay, so we don't store much of the water in Southern California. In urban environments, that means we have to increase our flood control. Okay? And I don't know what flood control is here, but we have a whole network of open channels that are basically, their goal is to get the flood waters out of the city so they protect us from the water. Now there's a new model that's being used to deal with these storms, is to infiltrate as much water into the watershed as possible. But the old model was just to remove the water out of the system as fast as possible. Okay, let's look at it in terms of water supply. So this is extreme events. Okay, let's look at it in terms of annual precipitation amounts. So we're going to look at how many wet years we have, how many dry years we have. Do we have more wet years or we have more dry years? Average precipitation doesn't change much. I don't have a plot for that. The projections of precipitation for Southern California and the western U.S. remain fairly constant. Okay, so rainfall now, or snowfall, I should say precipitation now is pretty much projected to be the same in the future. But what does change is the variability. Because we always talk about mean changes, and I've done that this whole talk, the part of the talk, changes in the mean, but what's really more important is changes in the variability. We have more variability that reduces our reliability of the system. Okay? So what we see here is our 50-year cumulative annual maximum flow events. Okay, so this is basically our 50-year sort of annual maximum event. But it's not on a daily basis, it's over the entire year. So this is a wet year versus a dry year. Okay, just rain. We actually do statistical analysis here, but and you see that we're getting more wet years. Great, right? No, because we're also getting more dry years at the same time. This isn't as, I won't look at the statistics on this field, but in general we see more yellows here, which means more dry years. Okay, so we have less normal years, okay, less years in Los Angeles. We happen to get allergic to centimeters real quick. 45, sorry, about 40 centimeters of precipitation a year. Okay, 40 centimeters is very little compared to here. You probably get meter here or something like that. 45 centimeters of precipitation. Okay. What it's saying is that we have more years where it's very extreme, very wet, maybe 8 centimeters, and other years where we have 5 centimeters. And that's actually what we're seeing today. Whether that's a result of climate change is still out for debate. What does that mean? It means less reliability in our system. Okay, how water resources managers peak uncertainty. Okay. We know it's going to be a wet year, it's going to be a dry year. How do we handle that? We have to lower our reservoirs a bit. This is last. Okay, we're in the most severe drought in history in Los Angeles right now. The reservoir managers, because we had an El Nino last year, all the reservoir managers were emptying the reservoirs. We're in a severe drought. They're emptying the reservoirs because they were expecting El Nino precipitation to come and flood us. Okay, so it didn't come. Now our reservoirs are even lower than they were before. So that's a very difficult thing to deal with the water resources management. So I'll conclude with a bunch of summarizing the two parts of the presentation. Okay? And I think just what I think are some take-home messages here. And depending on the greenhouse gas emissions scenario, average global temperatures are projected to increase by 1.5 to 5.5 degrees in 2100. Okay, so 1.5 we can deal with this by fairly resilient to 1.5 degrees. Most of our ecosystems. It's only the transition areas that are impacted by 1.5 degrees. So where you transition from, say, our snow line, for example, in the western U.S., it would move up, certainly would move up 1.5 degrees and move up the mountain, but the rest of the mountain may not be impacted. But 5.5 degrees would change the face of our planet in terms of our ecosystem. Over land, the increases would be 3 to 10 degrees Celsius. So actually 1.5, but really over land, those values are much higher. Okay. So that's, we have to really deal with that. Maybe about 2.5, 3 degrees on our low end, and up to 10 degrees Celsius on the highest. Okay. So imagine here today being 10 degrees warmer. Sea levels projected by the end of the century to be anywhere between 0.5 meter and 1.2 meters. That has impacts on the coastal system. And our current, okay, so what are we doing now? Okay, so what is our current emissions path? Okay, so we've had all these, the IPCC was set up in 1988, and every year, every time it comes out, they talk about a business as usual scenario. Talking about all these mitigation scenarios. We always follow the worst case scenario. Since 1988, we've been following the worst case scenario. At this stage, we are on our current emissions path to take us up to 10 degrees warmer than we land. Hopefully, we'll start to do something about it. The increases in temperature are likely to result in numerous negative impacts. And this is just a whole long list of things. Increased, so I just showed examples of some of these, but increased destructive weather events, okay, so more extreme events. We had Hurricane Sandy, we have a hurricane that's hitting just past Haiti, I believe, a couple of days ago. Increased deadly heat waves, I showed examples of that. And severe negative changes in the structure of many of our ecosystems that will result in extinction of many species in some short term. And the list goes on. And I shouldn't say that there aren't positive impacts to climate change. There's certainly an economist would look at this and they would want to know what the positive impacts are. Okay? And some of those are benefits to our northern neighbors here, and maybe longer growing seasons. That's a positive impact. That sea ice gone, okay, up in the North Pole, all the sea ice gone. That's great for shipping. Right? So you don't have to go through the Panama Canal. You don't have to be out here anymore. You can go through there. So the economists look at this and they do an analysis. Okay? And they look at whether it's better to do something about climate change or just go with business as usual. Okay? And what they usually find, plus or minus, is that more or less a wash. Okay? Do something now or wait till later. It's more or less a wash. Okay? And some will say that it's actually better to do something now. Some will say that. What I think to me is, so when I think of it in those terms, I think, well, okay, maybe not that big of a deal. At least I do think it's a big deal because I really do care about our ecosystems. But we can deal with these in our Western world, our northern neighbors, let's call it. Our northern neighbors can deal with these deadly heat waves and these floods. Okay, we can adapt to that. We have lots of money. We can build more infrastructure to protect us. We can build infrastructure to protect our coastlines and so on. We don't want to do that, but that's what we could do if we have to. But here in El Salvador, building seawalls, flood control channels, and more bigger reservoirs and things like that is probably not on the it's something that can be easily done here. And so what I feel like the biggest problem is with climate change is that the negative impacts would be disproportionately severe on some of the poorest regions of the world. Okay? So our northern neighbors, okay, which is me, right? We're emitting all the greenhouse gases per capita, but the consequences are paid for here in El Salvador, Maldives, or India. Okay, so it's important for nations and communities to understand. So this is what I think. This is a leading point that we have to understand the risks of climate change. We want to understand our vulnerability and our risk, okay? And develop the strategies to increase our resilience. Okay? This is a lot about what Prop 21 is trying to do. Is how to help our southern neighbors become more resilient to climate change. Okay, so this, and this is a point that I think that. We have these global models out there, the 3D user data are fully available. I don't know if anybody here has used them. We have all the output from these global models. And they can provide meaningful projections at large scale. They don't have the resolution the same thing you say about El Salvador, San Salvador, but maybe something about Central America. And as you obviously know, El Salvador is small, coastal, complex topography. So I'm just doing it for our guests here. But in those GCMs, the global models, we're talking about roughly a grid point or two. Okay? So the global models are saying 1 point represents the coast, represents here at, what are we at, like 800 meters or something? It represents the mountains where, the top peaks are growing. Regional climate models, and so I'm just going to make a pitch for the regional models, because these are things we can do on our PCs here. Okay? Any one of you can send these models up and start to make projections about climate change as a part of your master's thesis, and then say, what are your impacts? What are the impacts going to be on our water resources, floods, heat waves, and so on? Okay, and regional climate models are powerful tools that can be used to localize these impacts. What are the impacts for San Salvador? And they can be performed on PCs without supercomputers. Of course, it's much better to have supercomputers. So these simulations, like one of those sets, that one set of simulations I showed for the water resources, that was done with the fastest supercomputer in the U.S. and it still took a year to do all those. So we had 30 simulations in total. Okay? And but we can do these same projections. The other set of runs that I showed could have been done on a high-end workstation, like something that you might have here. It might take 3 months to run one simulation, but you could do it here, and that's normal to wait 3 months. Yeah, I don't know what your simulation is. And with that, I thank you for your attention. Hopefully I didn't eat into this time. I appreciate the organizers letting me go first. Thank you very much.
Agradecemos al Dr. Paul por su fantástica presentación. Vamos a dejar la sesión de preguntas hasta el final de las 2 charlas magistrales. Vamos a llamar luego a los 2 ponentes para que respondan preguntas en conjunto. Así que pasamos a nuestra siguiente presentación y voy a presentar a nuestro segundo ponente, el doctor Víctor Carmona. El doctor Víctor Carmona pues, nos ha visitado en varias ocasiones aquí en la UCA. Es uno de los principales promotores de la relación entre LMU y la UCA. Por eso también quiero aprovechar para agradecerle la generosidad y el entusiasmo con que promueve la cooperación UKMU. Él es un experto en ecología tropical y forma parte del equipo de trabajo e investigación de la Loyola Marymount dentro del Departamento de Biología. Ha realizado varias estancias en El Salvador como becario Fulbright y ha realizado trabajos de investigación conjunta con el programa de biología de la Universidad de El Salvador, lo que lo ha hecho merecedor de reconocimientos por parte del Instituto de Ciencia, Tecnología e Innovación de la Universidad Francisco Gaviria y de la Facultad de Ciencias Naturales de la Universidad de El Salvador. La investigación especializada es fundamental ya que brinda un sustancial aporte en la comprensión y la mitigación de cualquier fenómeno, y esto aplica tanto al cambio climático, como lo acabamos de ver con el doctor Paul, como a la erradicación de una enfermedad vectorial como lo es el mal de Chagas, de lo cual nos hablará el doctor Carmona. Nos vemos con el doctor Carmona.